So it is my pleasure to introduce our next speaker for the day. So that is Professor Susie Speller. She is a professor from the group of Material Science in the Department of Materials at the University of Oxford in the UK. And she's an expert in fusion and superconductivity. So we're really happy that you joined us today, Susie. And please welcome to the event.
Thank you very much. I'm just trying to figure out sharing my screen. I'm wondering, hang on, it's not now doing it.
Yeah, it's not yet in full mode, but at least we see your screen.
Okay, you see it. Good.
Yeah.
Right. Okay, can everybody see that? I'm just onto the right desktop. Do you see it in the right mode?
No, we see the other desktop probably. Now we see it. Yes, that's perfectly fine.
You see it?
Yeah.
Good. Fine. All right. Well, thank you very much for the introduction. I'm just now trying to get to the window that shows me everybody out of the way. Brilliant. Right. So as introduced, I'm Professor Susie Speller from the Materials Department at the University of Oxford. And I'm going to tell you today about some of our research that we've been doing recently, particularly looking at radiation damage of high temperature superconductors, which is a big concern for fusion, because obviously in any kind of magnetic confinement fusion, the magnets are a key component, and we use superconductors for those. So any damage that we get to the superconductors because of the interactions with neutrons produced by the fusion reactor is going to, we need to understand it. So just by way of a mini introduction, I expect this audience already knows a lot of this already. Obviously, you know about the fusion reaction. I don't need to tell you about that. And I expect will know about the conventional sort of roadmap towards getting fusion power plants, the traditional sort of timeline, where we're looking, ITER at the moment being built, demo being the sort of next phase beyond that. Again, still an experiment, but 1.5 times bigger in all sort of dimensions. And then first power plant later than that. And I think this timeline is probably being revised. I haven't seen the new one yet, being released yet. But the key that's driving this sort of increase in size potentially is that fusion power is proportional to the radius of the device to the power 3. So bigger devices produce more power. But they also depend on the strength of the magnetic field to the power 4 in magnetic confinement fusion. So if we could double the magnetic field produced, we could increase fusion power by potentially 16 times. So why does that mean that we use superconductors? Well, if you want to generate very strong magnetic fields without taking up too much space with the windings of the magnet, then you need to do it with superconductors. They just carry a lot more current density than conventional metals can. Of course, also along with that, you get lower energy losses because the DC currents at any rate are resistanceless in a superconductor. So you have to cool it down, but that's the only loss you've got really. And of course, because of this high current density, we can get compact windings. So that's why superconductors are used in all of the sort of next generation of fusion machines, including ITER and all the sort of demo concepts. They all use, all the tokamaks and accelerators actually will use superconducting magnets going forward. What else could we do though to try to speed up this timeline to getting commercial fusion? Well, instead of making the devices much bigger, which has a lot of engineering cost associated with it, as well as challenges for the engineering. What about increasing the magnetic field strength instead? And if we have a look at this graph, the X coordinate here is the temperature that we're operating our superconductor at, and the Y-axis is the irreversibility field. That's just the highest useful magnetic field that the superconductor can operate in. It still superconducts above that field, but you can't get any resistance-free current above that field. So you can see that For niobium-3 tin, which is a superconductor that's being used for the TF coils in ITER, you've got quite a relatively small operation window here. And that's why ITER is operating at, say, 13 Tesla there or thereabouts, and at 4 Kelvin liquid helium temperature. Now, if we move to a different superconducting material, for example, REBCO, rare earth barium copper oxide, you can see that it opens out a much wider operational space for you to work your magnets. And so this opens up the ability to operate at, say, 20 Kelvin, 20 Tesla, which is what the compact tokamak companies like Commonwealth Fusion Systems and Tokamak Energy and the UK STEP program, all of them are looking at operating in that kind of field and temperature regime. So they can't do it with niobium-3 tin, which is a conventional low-temperature superconductor, but they can do it using REBCO, which is a ceramic high-temperature superconducting machine. So as well as this sort of smaller machines, they're very much gunning for much more ambitious timescales to get power to the grid. Still talking about the 2030s, some of these companies, and the hope is that by bringing the scale down of these devices, that we can make them cheaper in the end. So I'm going to tell you a little bit more about the superconducting material, REBCO, which is really the only option we have for compact fusion, magnetic confinement fusion. It's got a complicated unit cell, which is shown on the left. It's got rare earth atoms, which could be either yttrium or gadolinium or dysprosium or europium. Any of those will work. Barium, and then the key part of the structure are the copper oxide planes. I don't know if you can see, I was going to get a pointer up. There we go. So the planes here, these are copper oxygen planes, and down here, that's where the superconductivity resides. So really superconducting current can whiz around on these planes, but it's much more difficult to get current to go along the C-axis of this unit cell up and down. It flows much better within the plane. The material is very anisotropic. You can see that from the unit cell. And so not only if we try to pass the current along the C-axis does it not work very well, but it's actually very difficult to get the current sideways from, even if you've got the copper oxygen planes lining up. If you have any grain boundaries, any twists like this, if you can see me in the picture, grain boundaries, so where you've got misorientations in your crystal like that, that will cut your current transport as well. It's very, very poor for getting current through this material. That stems from the fact that high temperature superconductors have very low coherence lengths. So grain boundaries act as a dam to the current transport. And because of that, we can't just make IBCO as a wire very easily. It's ceramic, it's brittle, so it's difficult to process in the form of long lengths of wires that we wind into magnets. It's very chemically sensitive, so it reacts with everything, and you've got to get the oxygen content exactly right for it to have good superconductivity. And you can't have any grain boundaries, so it's essentially got to be like a kilometer-long single crystal. So to make that happen, it's very difficult material science, but to make it happen, you make a material called the coated conductor, which is shown here. So it's got a metal substrate about 100 microns thick. It's like a metal ribbon. And on top of that, you deposit a series of oxide buffer layers. These aren't the superconductor, these blue layers in here. They're there to match the lattice parameters or to induce the crystallographic alignment that we need for the superconductor and to stop the superconductor reacting with the nickel-based substrate. The black layer here is the superconductor. It's about a micrometer thick. And then you coat it with silver, which high-temperature superconductors don't react with. It's the only metal they don't mind. And then the whole lot's stabilized with copper on the outside. So you have this multi-layer technology that's made by coating techniques, either chemically or physical vapor deposition techniques. And you can make them now in lengths up to about 1 kilometer. There are probably about 7 or 8 commercial manufacturers around the world, maybe a couple more now. In 2020, they're making about 1,000 kilometers of this stuff a year. But even this year, in 2024, they've delivered 10,000 kilometers just to Commonwealth Fusion Systems. So they've scaled up enormously the manufacture of this material because it's so critical for this compact fusion idea. In terms of performance, at kind of fusion relevant temperatures and fields, best we can tell you really, it can carry 2,500 amps per centimeter width of this tape, even though there's only 1 micrometer of superconductor in there. So that gives you just some idea of the enormous current densities that superconductors can withstand. But it's really expensive. Back in 2020, which is the last data I have available to me, it was about $100 per kiloamp meter. That is likely to have come down a fair amount with the scale up of the volume that's being produced. So that's the material we're talking about to make these magnets out of. This is absolutely straightforward for you. The idea here is that obviously we're generating these high energy neutrons. They're going to damage not only what you're probably more aware of, the first wall, structural materials and things like that, but they're also going to see the superconductor. And of course, in compact fusion reactors, particularly near the inner limb of the magnet, there's not going to be very much space for neutron shielding before you get to your magnet. So you'd expect quite a high flux of neutrons to be your superconductor to be exposed to quite a high flux of neutrons. So the question we've been asking for the last sort of over 5 years now really is, how long will the superconductor last? This high temperature superconductor that's very complicated, very sensitive chemically, how long will it last when it's hit with neutrons? There's a key bit of data that's available from 2018 on neutron irradiated coated conductors of this material. The left-hand plot here shows how the critical temperature of the superconductor, so the maximum temperature at which it superconducts, how that changes with the fluence of fast neutrons. And you see that for the different lines are just different commercial manufacturers, different products of coated conductor that are available at the time commercially. It's all scaled so that 1 on this axis is the original TC of the material, because they do vary a little bit. So it's all normalized to TC before you irradiated it. And you see you get this drop, this linear drop in transition temperature as you increase the irradiation. So the superconductivity is being lost as you increase the fluence. You also get an interesting effect in terms of the current density that the superconductor can carry. And again, it's been normalized, but you see that you get this enhancement before it drops off and starts to degrade. We understand why this is. This is to do with the fact that when neutrons come in, they form some damage in there, some sort of nanometer scale damage in there, which acts as what we call flux pinning centers. So magnetic field lines in superconductors get pinned by defects like this, and it stops them moving. And that's how you increase the critical current of a superconductor. So the key thing, though, is that it's going to damage in the end. Whether or not you get the enhancement, it's going to damage in the end. And if we put this onto a DPA scale, I think I've got it on a DPA scale here, convert that fluence into DPA. You get to the degradation region at about 4 milli-dPa, so four displacements per 1,000 atoms. So a very tiny amount of damage, and you're already caused 10% drop in TC. Okay, so they're really sensitive, these materials, to neutron damage. So looking a little bit at what happens when a neutron comes in, this is a simulation, molecular dynamics simulation that's been done by the group in Lancaster, Sam Murphy, and hopefully it will work. What you're going to see is essentially one event where one particle is coming in and hitting the atoms in the IBCO material, and every dot you see, coloured dot, is a atom that's been moved off its original lattice site or away from where it should be. Different colours refer to the different elements in the structure. So let's see if it will work. There we go. So this is one incoming neutron, and this is the cascade that happens as a result of it. These are about sort of 10 nanometers across. It's not labelled on there, but it's at that kind of length scale. So you can see a huge amount of damage in these cores here. This material in here is no longer going to superconduct. There's just far, far, far too much damage. Okay. We can see it. We can see it in TEM images. So this is a TEM image on the left. You can see the lattice planes of the matrix. This is the Rebco structure. C-axis is sort of this direction, if you can see my pointer. These regions here pointed out by the white arrows, these are amorphous regions where those cascades have happened, those cascade events have happened. And just out of interest, you can see it in some different imaging modes as well. It's not very clear in high angle dark field, a bit clearer in STEM imaging in bright field. You can see the sort of damaged region of the order of sort of 10 nanometers in size. You can see that there. But interestingly, these features these isolated damage cascades here don't explain the drop in TC. So that might not be clear to everybody, but transition temperature is measured by passing a very small current through the material and measuring where you start to see resistance. So you're not passing a big current through it at all, you're passing a very small current. So if there's any path through perfect undamaged material like this that goes around those isolated defects, you would expect to see the TC of that path. And so if you had perfect matrix and it only had these damaged regions separated in space, we wouldn't expect to see a drop in TC at all in our measurements. But because we do, we know that all of this material that still looks like it's crystalline is actually damaged, even though we can't see it in this kind of image. So I want to talk a little bit about the two flavors of research that we've been doing in my group as part of an EPSRC fellowship. I've got quite a large group of graduate students and postdocs working on this. If you look at the central diagram here, if we're trying to understand radiation damage in superconductors, we have a bit of a problem because obviously fusion spectrum neutrons are 14 MeV neutrons. There will be other energies of neutrons there as well, of course. But superconductors are going to be at low temperature when they're being irradiated. And we don't have any sources of fast neutrons, preferably 14 MeV neutrons, with high enough flux so you can do damage to the material in a sensible time frame, and where we can have the superconductor at low temperature. Because to get high flux of neutrons for damage, you tend to use a fission reactor, and it's pretty tricky experiment to do to put in some sort of cryostat into a fission reactor. So we can't really do the experiments under the conditions that we would like to be able to do it. What we can do is neutron irradiation using fission spectrum neutrons at room temperature or just above room temperature, so that there are some samples available, like the ones from Vienna that I showed you. There aren't very many others, but there are some of those. And of course, we can do with ions. Instead of using neutrons, using ions instead. We've got a huge range of energies available to us, and you can get to damage much more quickly with ions. And we can also do it cold. So I'll show you some of our cold irradiation experiments. The problem is that ions will not necessarily do the same damage as neutrons. So our questions really that we're trying to answer are twofold. What does temperature do? So when we irradiate cold instead of at room temperature, what effects does that have? And are ions a good proxy for neutrons, or which ions, under what circumstances, are they a good proxy for neutrons? Because we open up a great amount more experimental space if we can use ions rather than neutrons. Okay, so I'm going to tell you some of the experiments that we've been doing in those two areas, and I'm going to start with the sort of ion irradiation as a proxy for neutrons first of all. So going back to this transition temperature idea, these are ion irradiated samples. These have been irradiated with helium ions. If you have a look, the left-hand image shows a high-resolution TEM image of an unirradiated sample, and the middle one shows the same sample, a different piece of it, but the same sample after it's been irradiated to 10 to the 16 ions per centimeter squared with helium. We completely lost TC. There's no superconductivity left anymore after this irradiation. But if you look at all of the atom positions there, you'll see that they all look pretty much where they should be. It's a little bit patchy of the image, which suggests there's some disorder, but it's essentially everything is where it should be. But in this imaging mode, which is the one that's usually used for high resolution TEM imaging now, it's in the STEM rather than in the TEM. It's the high angle dark field imaging mode. And if you have a look at the right-hand image where I've zoomed it out a bit, in a bit, sorry, you can see that the only atoms you can see are the heavy ones, the rare earth, the barium, and the copper. We can't see the oxygen sublattice at all in this imaging mode because the atoms are too light. There's not enough contrast from them, not enough scattering from them. So the fact that we've lost TC, but all the cations look essentially to be where they should be, suggests to us that there is quite a lot of disorder happening and defects happening in the oxygen sublattice. And that feeds in quite well with some prior literature in this that shows that oxygen defects are easy to make in this structure. So since we can't see those oxygen sublattice directly using electron microscopy, we've been looking at other techniques that will help us work out what's happening to the oxygens. And one of those techniques we've been using is called X-ray absorption spectroscopy. It's used by chemists quite a lot with molecular sort of chemistry. But essentially what you're doing here is using X-rays at a synchrotron to excite the atoms in your sample. So in this case, the copper atoms excite electrons from the 1s shell into the 4p unoccupied orbital. And you obtain an absorption edge associated with that transition. And from that absorption edge, the near edge, this region here where you're seeing the change in slope, the features along there are sensitive to things like oxidation state of the copper, but also the bonding environment around the copper. So if you move the oxygens that are around the copper, you would expect to see changes in this near edge structure. We can also get information, although I'm not going to talk about it today, from the extended edge, which is after the edge. This is where you generate photoelectrons that leave the nucleus or leave the atom and get scattered by neighboring atoms, and then they interfere. And from these interference fringes, you can get geometric information about your structure around the copper atom. So we've got quite a lot of information in these kinds of scans. And it uses hard X-rays, so we're probing the entire coated conductor layer, the entire REBCO layer. However, analysing the spectra is pretty difficult for REBCO because if you look specifically, I've only shown the coppers and oxygens mainly here in the unit cell. You can see there's two different copper sites. There's the copper 2 site here, which is we call the plane site, and the copper 1 site, which is the chains. So you've got these chains of copper and oxygen along the B-axis. The coordination around those two copper atoms is different. So we'd expect the spectra, the near edge spectra, to be different from those two different absorbing atoms. But of course, when we do the experiment, we're going to see both of them together. So we're going to see a sort of average of the two. We are a bit lucky because of the crystallographic alignment of the material that we have to do to make it carry high current. And we can actually get some information, polarization dependent information. So depending on what direction our X-rays are polarized in, we can either probe the sort of bonding along the C-axis or in the AB plane, sort of differently, the electron density really in those two different directions separately. So that helps us a little bit. The edge looks something like this. I've only showing one of the polarization directions, but you can see it's pretty complicated. Lots of features along here that have been labeled. It's very difficult to work out what the origin of each of those features is unless you do some kind of modeling. So I've been working with Rebecca Nichols, who's a colleague of mine in the department here, to do DFT modeling of the REBCO structure and simulating of the absorption spectra from that DFT model. And this is an example of the modeling that we've done. The dotted line here shows the model, and the full line is the experiment. Don't worry about the intensities, they're completely arbitrary. But I hope what you can see is that we are reproducing the features at these different positions, A, B, C, and D, along the rising edge. So that's good news. The modeling allows us to separate copper 1 and copper 2 because we can't do it experimentally, but we can work out what components come from what in the models. So those first few peaks along the rising edge in this orientation are from the plane site coppers and have very little contribution from the chains. And you can see that you have to be further up the edge to get much contribution from the chain site oxygens. So that's a first sort of order analysis, really. If we now look at what happens when we irradiate the sample, this is the helium irradiated sample that's lost superconductivity completely. You can see the red line is what happens when we irradiate. So we get some really quite big changes in the spectrum. And we can look at the different spectrum on the top right when we take the irradiated one away from the pristine one, or the pristine one away from the irradiated one, actually. You can see the changes there. And most of the changes are associated with the plain site coppers that we're seeing. And that's really interesting because actually people thought that it was the chain oxygen that was easiest to move around and that most of the defects would be in that site. And we've got some really quite clear evidence that we're getting defects in the plane as well, the copper planes. We can do much more complicated things than this if we like, because with DFT modeling, we can put particular defects in. We could make a vacancy, or we could put in a Frenkel defect, and we could model what the spectrum should look like. And we can compare that with the actual changes we get on irradiation. And if you want to know more about that, you can look at the paper that's referenced at the bottom, the Nichols et al. Paper, where we've done some simulations of some defect structures. So how does this help us with understanding whether neutrons are a good proxy for ions, or ions a good proxy for neutrons? Well, we can reproduce this experiment using neutron irradiated samples. So these are some samples that have come from the Vienna reactor, the Trigger reactor in Vienna. They're ones that featured in that paper, that sort of seminal paper I showed you with all of the main data of neutron irradiated samples. And if you look at this plot, these are just difference plots now in the two different polarization directions. The blue and the green at the top are the neutron irradiated sample, and the red one is the ion irradiated. And even though we put a lot more damage in, and so I've scaled the sort of the scales are not quite the same on the y-axis, you'll see that the features are pretty similar. That when we do the neutron irradiation, we get pretty similar spectral changes than when we do the the helium irradiation. And that does suggest to us that we're putting in similar kind of defects. So that's quite nice. That's some evidence that we've got that the helium ions are a useful proxy for neutrons. We've got some other evidence that's quite interesting as well. And this is looking at the fractional change in TC, so how TC changes with DPA. And we can you do this from the literature here, the neutron irradiated samples that I showed the data for, some proton irradiated from MIT, and some of our own 2 megaelectron-volt helium irradiated samples in black. And if we scale on DPA, we see we get a pretty much universal curve for how TC degrades with damage. And so this is another piece of evidence that actually neutrons and ions and protons are doing a similar kind of, at least they're damaging things at a similar rate, which is interesting. So moving to the second kind of experiments that we're interested in, and this is what the effect of temperature is, we've got some ion irradiation experiments that we've done in situ. So here we go to Surrey Ion Beam Centre, where we can irradiate with helium, for example, our samples. We make a narrow track of the superconductor. So the black stuff here is the superconductor. We pattern it into a narrow track. That's just so that we can reduce the current we need to stop it superconducting, makes it easier for the experiment. We mount it on the top of a cold head here, and then we put it under the beam. So we can have this cold at 40 Kelvin, we normally do our experiments at, and it's cold when it's being irradiated, and we can measure its superconducting properties via a full probe transport measurement at the same time. Some of our data is shown here. So this is the cold irradiated data. This is scaled from the initial to normalized to the initial current density of the track for several tracks here, irradiated cold with damage converted to the DPA scale again. You see you get this degradation immediately, and it's pretty similar for all of our different samples. If we compare with room temperature irradiation, we actually get, there's a little bit more variability in the room temperature irradiated samples, but the rate of damage is really quite similar. But there are some really interesting differences that I want to highlight. So if we cold irradiate and measure whilst it's cold, this is the data that I'm showing you here, the blue data I'm showing you here. But what we can then do is we can warm the sample up to room temperature again, and then cool it down ex situ and measure TC again, or JC again here, okay? And when we do that, you see we get some recovery. So this sample here had this JC when it was tested cold during irradiation, or just after irradiation, actually. You warm it up to room temperature and then remeasure by cooling it down again, and look, it's got better. Quite a lot better, actually. And we've got various examples of that where we've done this room temperature anneal. And we've then, with this sample, we've just gone and done some more damage afterwards. And we see we degrade it again, and then we can improve it again. So we can do this partial recovery. So actually, I think that the damage landscape, the defects that are there in the room temperature irradiation and the cold irradiated samples are probably not the same. Because clearly we can recover some of the damage when we irradiate cold, and we can't do that when we irradiate at room temperature. People are interested, often ask this question, which is, does that mean we can extend the lifetime of the superconductor by just intermittently warming it up? I don't expect any reactor designers are going to want to use that as a strategy for keeping their lifetime of their superconductors up, but it is quite a useful corollary, I guess, that you will have maintenance cycles, and it might be that it does mean that your superconductor doesn't degrade quite as fast as it may otherwise do. So what about these defects then? Well, this is a bit of hypothesis really about the fact that the damage landscape probably contains defects that have different activation energies in terms of mobilities for getting back and recombining and annealing out. And at low temperatures or room temperature, we can probably anneal out the low activation energy defects, but not the higher energy defects. And so it just explains why we might get partial recovery. And then also if we anneal above room temperature, provided we're careful not to lose oxygen from the sample, so we normally do it in oxygen, we can actually recover a bit more and improve it even more. So that there'll be the higher energy activation energy defects. So I think I'm probably nearly out of time. I want to just tell you our next steps. So we're looking at other TEM-based techniques for trying to visualize the oxygens, because we can't do it in the conventional imaging mode. So we're looking at some electron tychography, and here's an example of some of our preliminary results. The sort of purple atoms you're seeing in the darker ones, they are oxygens. So we can now image them using these really high-end techniques in collaboration with people at Diamond and the EPSIC facility down at Diamond. We're also doing some cryoirradiation using fusion spectrum neutrons at ISIS in a facility called Nile. The problem with this is that they're very low flux experiments. So we're not trying to damage the superconductor and look at the permanent damage. We're trying to look at whether the superconducting state is sensitive to impacts from neutrons, and whether those impacts are going to cause some problems to the superconductivity in situ during the operation. Interestingly, on the right-hand side here, we're also looking at higher field properties of superconductors, because cotoconductors are very rarely measured at the operating conditions that we're going to use them at in a tokamak. And so we want to understand their much higher field properties using facilities like the Pulse Magnetic Field Facility at Los Alamos. And so we've done some preliminary experiments there, and we've got more coming up in a couple of weeks' time, actually, to try to really understand what's going on at the kind of fields that we're going to be operating these magnets at. And that's all that I was going to tell you about. So why we're interested in this material REBCO for compact tokamaks, and some of the work that we're doing to try to understand how long the material is going to last in service in a tokamak. And I'll leave up there the acknowledgement slides, lots of people at lots of different places, and the funding, of course, from Engineering and Physical Sciences Research Council. Thank you very much.
Susie, thank you very much for this excellent presentation, not only on the challenges of superconducting magnets, but also the challenges of operating in a nuclear environment, which brings a lot of complications and new issues to solve. But thank you so much for this. We have 2 questions for you. So in the sake of time, I will ask one live now, and then the second one, both of them are in the chat. So you would have some time after this if you can address the second one in the chat. But for the moment, I would like to ask you the first one. So it's why are the helium irradiated spectra smoother than the neutron irradiated spectra?
It's a good question. So we did the neutron damage in terms of the DPA, equivalent DPA, was much lower So it was a far less damaged samples. So the difference spectra, when you're comparing to pristine, they were much closer together, much smaller absolute differences. So on that particular graph, I'd scaled the axis. I can't remember. I think by 0.15 or something. So something like that. I've written it on there. I can't remember quite. We can go back and look. Just because the amount of damage in the helium irradiated sample was so much more. So that's why it's smoother, because the absolute differences were much bigger. So it's just noise. Noisier, the neutron one.
Okay, thank you very much. So if you have the time, please check the chat of the event. There is a second question. If you could address it in the chat, that would be great. Thank you so much, Susie, for joining us for this event. It was great to have you here.
No problem at all.